continue our sort of foray into the world of the atom and the electron. Now, a favorite question, if you remember when I was talking about the EMF of the cell, we did an experiment with a rheostat, and we then drew a line, and we then extended the line back, and we found the y-intercept was the EMF. And remember, now in this one, I sort of said you're either going to get that as a question or the one in the photoelectric effect. And here it goes. This is an whoops, back to my proper color. And here we go. This is the experiment. So in the photoelectric effect, you're given an experiment, right? And what they tell you is they give you a certain amount of energy, coordinates, EK, and they also give us some frequencies in hertz, okay? So they give us essentially ordinate pairs. What do we do with this? We go and we draw a graph. The graph that you draw is the following one. Let me just give me a little space. Okay, you draw the following graph. Okay, and I'm going to put it like so. And you plot the points. I'll just plot them, the points you're given, and that essentially is the graph, right? And we always plot up here EK, and over here we plot frequency. This is the x-axis, that's the y-axis. And those are the actual results, right? Those are the results. Now, yes, once again, we are going to do what we did before. We are going to extend this line backwards, and we're going to now look at 2 points. Can you see at this point, this is when y equals 0, correct? And this is when x equals 0. And this line here is a straight line. Okay, let's examine this thing, okay? Because it's always good to know where it comes from. We said that, remember, HF is equal to W0 plus EK, correct? Right? Therefore, minus EK is equal to minus HF plus W0. Therefore, multiplying by minus 1, I get EK equal to HF minus W0. Now I'm just going to put in over here y equal to mx plus c. X is the frequency, y is the kinetic energy. Let's go and check. Here we go. Yes. Can you see y is the energy? X is the frequency. So we've put it into a straight line format, haven't we? Now, what do we do with this now? Well, what we do with it is we can say, at the various points, let's have a look what happens, okay? I've just said here, if y equals 0, therefore EK equals 0, therefore, I'm just going to put into the equation, 0 is equal to HF minus W0, therefore W0 is equal to HF. So at that point there, I've said the EK was 0, so where am I? I am over here. Let me just maybe do it in red. I am here. This is where EK is equal to 0. What have I got? This is actually my F0, the threshold frequency. Okay, that's as simple as that. That's all it is. Well, this is where x is 0, and this over here is going to be equal to WO, is the work function. Right? Let's have a look. Let's put it in. Let's say x equal to 0, all right? That is where, all right, my frequency is equal to 0. So what do? I say, right, that's the energy that I need to haul it out, which gives me, let's just put it in to the thing, is x equal to 0, y is equal to m times 0 plus c. In our case, it's going to be ek is equal to H, which is a constant, times 0, okay, minus W naught. So the energy that I read there is equal to minus W naught. I'm just going to break it apart. W naught. Okay? So the work function is represented on the graph by the intercept here. This is the work function. Over there. Work function is there, and that's the threshold frequency. Okay? Now, that's a very favorite sort of one that is often asked in a test or an exam situation. Let's move on up and look at the photoelectric cell, shall we? Photoelectric cell. This is often used, and what you've got is you've got a scenario like this, like that, and I'm just, excuse my drawing, as I've said, I'm not an artist, but here's my cell enclosed over there, all right, and it's enclosed in a vacuum tube. All right, so it's inside a glass container, and we've got this here connected to the plus, and this is connected to the minus. All right, now this over here is the cathode, okay, and it's made of photoelectric material. Okay, in other words, it's made of a metal that will emit electrons when an incident light falls onto it, correct? That's what it's there for. Now, let's have a look at some of the scenarios. Whoops, just move this guy up a bit more. There we go. Let's have a look at a few scenarios, all right? Let's have a look. Section 1, no incident light. Okay. Well, if no light falls on it, okay, the electrons stay on the cathode, don't they? They're not going to go anywhere. They just stay where they are, because this is my negative side, that's the positive side. Okay? So there is no, the electrons are all there, but there's no energy for them to go anywhere. They just stay where they are. So no, nothing is going to flow through it. Now section 2 is we irradiate with an incident frequency or a wavelength, right? Remember, if you get given lambda, you convert it to frequency straight away from C equals lambda F, all right? Now, what happens? The light causes the electrons to be emitted. So we've now got incident light. Let's move up. So let's have a look. We've got incident light. All right. So what happens is electrons are emitted. Okay. Emitted means given off. Okay. So what happens? All right. Then they can move across the space. They move across space to the positive. I've got my positive, and here's my electron, my negative side. So what happens? The electrons then move across there because the positive attracts the electron, which is negative. So it moves across the space to the other side. Now, when that electron gets there, more and more are on their way. So what does it mean? It means that the current starts flowing. So when the light shines on it, the current starts flowing. Now, obviously, you can get it the other way around, so that when the light stops falling on it, okay, the current can flow as well, right? You're just going to reverse it, okay? So let's have a look, all right? All right. Please remember just to know the definitions of work function. I just made a note to myself. Now, let's just do an example over here, okay? Let me do an example. Okay, we have got the following light sources irradiating a photoelectric cell. We have got red, all right? I probably should have done this. Come on, let's do it in a let's do it in color. Red. So we've got red light over here, and they've said the wavelength of the red light is 650 little n m. Little n means nanometers. Okay, then I've got green over here. Green light, okay, and you can see that darkness, if it comes across to you, is because I'm blocking the light onto the screen. Okay, lambda equals 540 nanometers. And lastly, I have got, I'm going to be using this, but I'm going to say this is ultraviolet. And I'm going to say its frequency is 1000 TH. Let's just see, hang on, T is tera, all right? How do I deal with a tera? Well, we'll get to that when we get to him, okay? Okay, let's now move it up a bit and see, right, what is the question? The question here is A, calculate the energy of the incident red light. So it's first of all, calculate the energy of the incident red light. In other words, they want the energy of the photon, right? So how do I do that? I say E equals HF, right? Okay, they say that energy incident red light, and hence show by referring to the work function that an electron will not be emitted. Calculate the incident, the energy of the incident red light. So the energy of the red light, energy incident, is equal to HF, which is equal to 6.63, okay? 6.63 times 10 to the minus 34, okay? Multiplied by the frequency, all right? Multiplied by the frequency times F. Now remember I said to you, look, the red light we've been given lambda equal to 650 nanometers. Nano n means 9, okay, which is 650 times 10 to the minus 9. We always convert it to meters. Why? Physics, that's what we do. Kilogram meter second. So we say, okay, that. Now I just need a frequency here. I know you can use the other equation if you want to with the wavelength. I just say, all right, just as practice. Whoops. Okay, and then you would say C is equal to lambda F is equal to 3 times 10 to the 8, that's the C, speed of light, divided by 650 times 10 to the minus 9, and I get a frequency of 4.615 times 10 to the 14 hertz. So therefore, my energy of the red photon is going to be 6.63 times 10 to the minus 34 multiplied by 4.615 times 10 to the 14, which gives me 3.06 times 10 to the minus 19 joules. And yes, you would be correct in saying that that is a very, very small amount of energy. It is. Okay? We're going to see what that can do now, though. Right. Now remember, they said here, okay, it is noted that an electron is emitted when green light is incident onto the surface. So hold on. Just let's read in the blurb. They told us that when green light is emitted, they said to us here, okay, when green light is incident, an electron is emitted. So what do we know about the green light? Well, we know that the lambda of green is 540 nanometers, which is 540 times 10 to the minus 9. We know that, correct? Okay. So therefore, what does that mean? The energy of the green light, let's just work it out. Okay. Once again, I need to find the frequency, and the frequency is 3 times 10 to the 8 divided by 540 times 10 to the minus 9, which is then going to give me 5.55 times 10 to the 14 hertz. Therefore, the energy of a green photon is going to be equal to 3.68 times 10 to the minus 19 joules, 6.63 times 10 to the minus 34, multiplied by, 5.55 times 10 to the 14, gives us 3.68 times 10 to the minus 19 joules. What does that mean? All right. Okay. That means that it's emitted. All right. That probably in the question is actually the work function. But let's have a look. The energy in a green photon. So it needs that amount of energy to be emitted. Now let's go back and say, but hang on. We've only got 3.06. Let's look. The energy of the red is equal to 3.06 times 10 to the minus 19 joules. It's not enough. It's not enough to get the electron. All it's doing is it's hitting the electrons up inside. We're going to deal with that now. So what is that done? It hasn't emitted an electron with the red light. Okay? Because I need 3.68 times 10 to the minus 19, which in effect is my work function. Okay? The next question, I hope that's making sort of sense if you think about it. The green is shone on, that got the electron emitted. Okay? In other words, it got it out of the material and ready to rock and roll on the outside. Now, the next question is to say, right, all right. Okay. Oh, and also don't forget, just let me go back up here. I made a note to myself just to explain here. Remember, this is also F0, the threshold frequency, right? So the work function and the threshold frequency. Because that's when they say it's emitted. That's what they mean in the question. Okay. The next question is, a higher intensity of red light is now shone onto the surface. Explain. What are they saying? Okay. They are saying that higher intensity red. Question 2. Whoops. Sorry. I wanted to say high intensity red is now shone. What does that mean? Which means it's got lots and lots of photons coming in. All that does, one photon goes to one electron. What does it mean? In this case, we've got 4 electrons are affected. Okay. We do not get them going out. Okay. Therefore, still no current. Why? Because F of the red is less than the F of the green, which is my threshold. Okay? There's not enough energy in there to get it out. So I can keep shining this infrared light on and nothing will happen to it. Okay? Then they say, oh, okay, nothing's going to happen. All right, then the last question over here, let's just get to this. Question 3 part is, they say, what is the velocity? What is the velocity of an electron if we irradiate with ultraviolet, also abbreviated to UV light? Okay, what is it if it's to UV light? Well, quite simple. What do? We're just going to say, right, now we say HF is equal to W naught plus a half mv squared. HF is the energy in. Remember, this is energy inbound. This is energy to get it onto the surface. And this is energy to make it go. So the energy in was 6.63. Okay, times 10 to the minus 34 times, and now we said the frequency is 1,000 terahertz. Okay, and tera is going to be 10 to the 12 is tera. So therefore my frequency is 1,000 times 10 to the 12, which is 1 times 10 to the 15. So times 1 times 10 to the 15. My work function was 3.68 times 10 to the minus 19 joules. Remember that. Must be equal to a half mv squared. Oh, sorry. Not that. Plus a half mv squared. My bad. Is a half times the mass of an electron. 9.11 times 10 to the minus 31 kilograms times v squared. Where do I get that come from? It's ME, rest, electron mass at rest, rest mass. It's given to you. In your table of constants, on your paper, you are given this. Okay? Right, now what happens? Well, now I'm just going to solve for V, aren't I? Yes, and they're small numbers, and where does this go wrong? Yep, calculators. So therefore, V squared is going to be 1.295 times 10 to the minus 18, 1.295, divided by 4.55 times 10 to the minus 31. Okay, and that's going to be equal to 2.843 times 10 to the 12. Okay, so my velocity, take the square root. Remember, this is squared, so V must be the square root of that is 1686. Okay, 128.6 meters per second. That's 1.6 million meters in a second. It's pretty darn quick. Okay, so that's quite straightforward. Okay. There's not a problem with those. Now what happens if the incident light, okay, all right, we've got, what happens if, let's ask the question, what if the frequency is less than the frequency, the threshold? So we are shining light coming in over here, but the electron is actually staying inside. Okay, this means the electron stays inside the metal. Let's just keep it with metals. Stays inside the metal. All right, that is what is happening there. All right, now the energy is actually going in. Now, do you remember we had what we called here the ground state? I'm sorry, I'm covering it up. We have the ground state of an electron. Then we had various levels of excited states that an electron could go up to. This up top here being the surface of the material. Okay? So just bear with me. It's not absolutely, but just think of it in this kind of analogy. The electron is sitting here. He gets bounced up there. Boom. Can come back. Right? The electron could go to any one of those states. It could fall all the way there, or it could fall in different steps down. Right? So there's a different levels that the electron can fall, right, from ground state. Now, in this scenario here, all right, we say that the energy that's coming in is just, remember, it's just rattling the balls in the triangle, but inside it's bouncing electrons up. It is absorbed. So the electron is absorbing and it moves up the orbital And each of these jumps is equal to HF. Because, remember, one photon and one electron. So that photon interacts with that electron, and if there's sufficient energy, it can move it up to there. All right? That's all it's going to do. Now, what happens when, say we've got an electron over here and it drops back there? Well, when it drops back, all right, remember, it drops back and it emits energy, but that is equal to HF as well, right? But just a second, frequency is linked to color. So each time it jumps back, all right, maybe that's going to be a green given off. And it's going to go up, and up top there is a blue. And right at the top is ultraviolet. It's not very neat. Is ultraviolet and gamma rays. So the energy in the gamma rays, if you remember the ultraviolet, is higher than in red. So as it comes in, it can lift it, assuming it can't get it out. Okay, it's less than the work function. It lifts it to different levels. Okay, now obviously in a gas, okay, we're not talking about getting it out of a gas. We're talking about a metal photoelectric. In a gas, it will ionize it. It will remove the electron from the atom itself. So now let's just look at what inside the atom, all right? We've got different energy levels. Remember we had the orbitals, all right? Now we're not going to go into all of this, but let's suffice it to say that we call them n equals 5, n equals 4, n equals 3, n equals 2, n equals 1. Okay? Can you see there? There is our different energy levels. Okay? Those are the orbitals as far. Now, if the electron is far from the nucleus, yeah, it's got 0 EP. Okay? So outside of the nucleus, it's got no potential energy relative to the nucleus. This is just how we define it. So as we go down here, okay, the energy gets more negative. The energy gets more, but in a negative number, all right? Don't stress about the negative or whatever at this point, okay? It's not absolutely critical. Just know that it gets negative the closer you get to ground state at the bottom, okay? Now, because the potential, let's say the potential is decreasing, okay? Okay? Now, at certain energy levels, we've got certain numbers, all right? Over here, the energy of, let's say, at n equals 5, I've done a few, n equals 4, just bear with me, n equals 3, n equals 2, and down here, n equals 1, all right? Like so. I've got energy levels here. This is minus 0.87 times 10 to the minus 19. This is minus 1.36. This is minus 2.42. And this is minus 5.43. And down here, minus 21.76. And it's all times 10 to the minus 19 joules. All right? So this is my energy. That's the energy level, energy state. All right? Now, let's say that's for each step we can fall, we lose energy. Okay? Now, when we fall, we lose energy. Think of it as steps. As you go down from the 1, you go from 4 to 3, you're going to lose the energy. All right? That's the easiest way to think of it. That helps you not to get baffled by the signs. So let's say we go from, an electron falls from energy level 5 to energy level 3. All right? So that's going to be E5 minus E3, which is going to be minus 0.87 minus 2.42. Okay, all times 10 to the minus 19, which gives us 1.55 times 10 to the minus 19 joules. All right. Now they say to us, when this happens, what color of light do we get? Well, hold on. We know that the energy that we lost was 1.55 times 10 to the minus 19. That must be equal to HF, right? Therefore, that must be equal to 6.63 times 10 to the minus 34 multiplied. Therefore, the frequency of the light that's emitted by falling from step 5 to step 3, okay, is going to be 2.33 times 10 to the 14. Okay, times 10 to the 14 hertz. Okay, let there be light. All right, which is equal to 233 terahertz. All right, and once again, if you want the wavelength is equal to 3 times 10 to the 8 divided by 2.33 times 10 to the 14, which is 1.28 times 10 to the minus 6 meters, right? So you can see that is the frequency of the light. Essentially, if they gave you a spectrum, you can say what? Color. All right? Let's have a look. Here's another one. Let's say we fall from E5 to E1. Okay? Let's take E5 to E1 is minus 0.8, okay, delta E, minus 0.8 times 10 to the minus 19, minus 21.76 times 10 to the minus 19, which is going to be 2.089 times 10 to the minus 18 joules of energy is emitted. Okay, if it's positive, it means it's emitted. Okay, negative means you have to add energy to absorb it, right? And we say that therefore E is equal to HF. Therefore, 2.089 times 10 to the minus 18 must be equal to 6.63. That's HF, right? Times 10 to the minus 34 times frequency. And the frequency of light I get is 3.151 times 10 to the 15 hertz, which is ultraviolet. It's UV light. Okay, it's UV light. So yeah, when you get one of these, now obviously, if they say how much energy do we need to go from 1 to 5, you would do it the other way around and get a positive. Okay, so just look, when you're dropping, you must be getting a positive, you're getting energy back, so it's plus. When you put in to go up the stairs, you use energy, it's minus. Okay, that brings us to the end of the syllabus. As you know, we're going to be adding content over the next years and months and years. We're going to keep adding, and hopefully we'll get questions and we'll do more research, and we'll try and stick as many exam questions as we can into the physics syllabus as added content into the site. Thanks for watching. I hope that you enjoyed the physics section, and good luck in everything when you get to the exams. Please go back, use this, go through the examples with me, make sure you understand, and all the best for the future. Cheers. Bye.